boosts are. Shall I just wait until that's.
The Lorentz boost is going to need the quadravector, isn't it?
I don't know if it did. That was the thing, is that if you look at the general form of like K, which is what you guys call it, and what you have also for it just in the literature, it's still, because you're expanding it in terms of an exponential, so you end up with hyperbolics.
Yeah, with Koshas and shines. So you never go. You never go.
So you don't get the quadravector. You do have pivot again, but you have pivot plus a space-time bivector.
I think thinking about it, you probably have the quadravector at the point where it switches direction on a reflection.
So, but then in terms of my decomposing stuff,
you can't do. Yeah.
If you decompose things to be in terms of the bivectors and the time-like element, the singlet elements, which is what I was saying previously, then at that point you bring the quadravector in there. But for the exponential, you have pivot and the space-time bivector.
Which is another copy of the Quaternions, but a copy of things that aren't quite Quaternions, of course, because
it's Quaternions, which are the handednesses.
Hyperbolic Quaternions. We probably want a name for that. Probably is a name for that.
I think so. There's tons. There's like Quaternions, biquaternions, split biquaternions, dual quaternions, all this kind of stuff. But
there are. You're right.
But you end up with this kind of fun stuff.
Flavors we have. But that is pretty fun.
But there we go. I haven't written it up properly. So that was the
Koshas and shines. Yes.
Koshas and shine one. So you end up with that. So your boosted wave function is. So you're doing.
You're using 1 for P.
No, because this is the generalized multivector.
It's just the maths.
No, so the way I'm doing this is this is a generalized multivector, so this is all 16.
All right.
So I'm saying you have a weighting in front of the 16.
Oh, that's just a weight. So that's just a real number. Yeah.
So your original multivector, whatever the form of that was, you keep, but weighted by that. Here
what's that Kosh acting on? That thing, is that a Q?
This thing here.
No, that thing. Yes.
That's an eta.
That's an eta. Aha, that's your eta.
So eta arctan.
That's one of those. Okay, right.
But you end up with
Okay.
You end up with this being sort of a weighting on the original multivector, but you've got these kind of, because of the sandwich, you're negating some of the elements.
Yeah, and
then your commutator of your boost plane here shows up at that point.
Okay, right.
Which is the same relationship as with the rotation. You end up, it's just that you swap sine and cosine for
the hyperbolics. Yes. Good.
Which is kind of fun. Good. But it's I just like that out of that sort of Lorentz boosts and rotations end up with these almost the same mathematical form, which is kind of
fun. As they should.
Yeah, which is good. They just sort of pop out as a thing.
So that's what you're doing for amusement late last night.
Yeah, I'm a nerd. I know.
Fantastic.
But it was just the thing that was driving me mad was that thing of, and you take a rotor, and I was like, but they don't work. They don't work on their own, like they at all. Like you can't. And so in terms of the thing that was really finding interesting is that saying pivot is what confines the electron and gets you your rotation. It's like you need pivot to rotate at all. Like unless you want to flip 180 degrees, like you need pivot to do any form of rotation.
There's something in here which is also pretty important and pretty subtle. You've picked up a question there, which is a very interesting one, and sorted some of that out, which is one that comes from the Cambridge group's worry about doing general rotations, and that formula for the sandwich rotation is something which they use for the simple sandwich, and you picked that up from somewhere where Martin and I put that down. God knows how long ago, 20 years ago, 15 years ago, which is pretty cool, which is pretty good.
Yeah, sorry.
Yeah,
I was just going to say.
In the current, what were you going to say?
I was going to say that from what I'd been looking before at the metric, the fact that you have those three parts, you have kind of, here's a weight on the original multivector, a weight on the sort of sandwiched multivector, which will negate some of the parts. And the commutator bit, obviously the weight on the normal multivector, that is just a weighting. So regardless of how you set up the algebra, that's just a scale factor.
Yeah.
The commutator is independent of the metric. So all the commutator relationships are completely independent of any metric that you set up. So the kind of effect of the metric on rotations is kind of contained in that sandwich element that's in the middle. And I think we might be able to look at that to help whittle down the list of algebras that are candidates, because I suspect that you're going to end up with that not doing the right thing in some cases if you don't have the algebra set up correctly.
Okay, so what that would mean is it means that the kind of experiment you need to do in order to get a handle on that is something which is rapidly moving at the rate of the system under study. Now that's hard for individual particles, and it's challenging because the rate's 10 to 21 hertz, so you can forget about humans measuring that. And it's challenging, but probably not impossible for atoms. So, because then we're down to sort of light oscillation frequencies of 10 to 15 hertz, I think, for those. So at least 1,000 times better off. Maybe it's 10 to the minus 18. No, 10 to the minus 18 is that would be nuclear stuff. Nuclear rotations, magnetic fields, yeah. Spin polarized scattering as usual. That's what it is.
But just because that kind of sandwich operation is the effect that has on things is going to change on the vectors and the trivectors, I think, slightly. I'll double check, but I can't remember if that's one of the ones that's independent of the metric or not. But I suspect that what you will get is you will end up with different. No, it's not going to change the handedness, is it? I'll have a look, but I think
it won't change the handedness between E and B. No, and that's
no, not between E and B. But I'm saying that if you're applying that rotation to a general multivector, then you're potentially going to have some differences.
Yes,
in terms of what you
potentially, but maybe not, because I think the rotors are effectively up to a definition. They're
oh no, yeah, by definition they leave it unchanged.
They're right-handed, yes.
Okay. Yeah.
Yes. So
maybe not.
Yeah, but that needs looking at. That's off the top of the head kind of thing. You need to sit. You need to sit down and do the maths here.
Crunch numbers.
I was going to volunteer. No, okay. Well, I might look at that anyway. But look, the whole thing's also associated with what's happening with the commutator and moving to commutator things. And the comment I was going to make before is that what we have in the algebra is written down and the equation is written down. The Williamson-van der Mark equation is something which is implicitly ordered. That is, the operations always introduce a 90 degree, a pure rotation.
Yeah. But that was the thing that was getting me with this, is that I wanted 90 degree rotations, not 180 degree rotations. And you can't do that with a pure bivector. You have to bring in pivot, which I thought was very interesting.
Okay, yeah, interesting indeed. Right, could you stick that couple of pages up on a file for me, or stick it?
Yeah, I'll take some pictures and upload them to
Slack or something.
I will. I can't take pictures at the moment because I'm using my camera for this.
No, that's okay.
I'll take pictures and send them to you. Send them to you later.
John, would you just take a moment and speak out what Innes just discovered about your math?
Okay, right. I'll try, and Innes will correct me if I make any mistakes, which is a lovely position to be in. Okay, I love it. Okay, right. The thing is that if you have a look at the subalgebra, so you have an algebra. It's a 16-component algebra. Now, in that algebra, different things represent different sorts of directions. So the simplest ones are the vectors, and the vectors represent x, y, and z. So that's alpha 1, alpha 2, and alpha 3. And time. So they represent a unit elements of space and unit elements of time. Now, these things are unit in the sense that they are, for the structure of space-time, they represent a a unit vector in the sense that a unit vector of space divided by a unit vector of time is the speed of light. That's the ultimate speed. So these are elements that have the property that amongst each other, they also contain the limits that are imposed by relativity. And that's the same limit whether you have plus, minus, 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 which is the Dirac metric, the metric that most physicists use, or minus, plus, 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 which is the metric that most astrophysicists use, that most cosmologists use. So relatively, they're different to one another. One's plus, one's minus. And that introduces a geometry into space-time, which is the geometry of general relativity eventually. But introduced here in special relativity. And it's deviations from that geometry in general relativity, the extent to which it is not equal to 1, that division, which is what gravity is in general relativity. It's a factor by which that varies. So we're looking at manipulating the structure of space and time here. Now, coming back to the algebra, if you now perform these kind of divisions, these kinds of divisions of space by time and so forth, you end up in different spaces, because in doing the division with something that has an intrinsic absolute relativistic form, by doing that division you either switch from a vector by a vector, you get elements that switch to bivector space. So for example, dx by dt is space divided by time, is velocity, is a bivector in that space. However, you can also divide space by space, and you get another kind of bivector. If you divide x by y, you get something which is essentially a sort of elementary rotation in the xy plane. It's a unit. It isn't just a rotation. It is actually what it is. It's a unit bivector. It's a unit space times a unit perpendicular space. But if you act on that from the left or right on any object, so if you hit any other object with one of these things, what it does is, acting from one side, rotates it left, and from the other side, rotates it right by 1 unit of rotation, which is 180 degrees in spinor space or 90 degrees in space. So these things are rotors. They're things that rotate things, but they are ordered rotors. So if you hit this with just an object with any magnitude with a specific bivector, so if I hit, let's choose an example. If you hit something in the xy direction with alpha 1, 2 from the left, it will rotate. So if you have something at 45 degrees to the axis, hit it with an alpha 1, 2 from the left, it'll rotate it anti-clockwise to the minus 1, 1 direction in a Cartesian plane. That's what it does. And it does that for all vectors that are aligned with that 45 degree thing. So, and all multivectors. So it'll do that for a magnetic field, for an electric field, for an angular momentum, and for a vector. It does a rotation. Like in the complex plane, if you hit something with I, so it takes a real number and rotates it in the complex plane by 90 degrees. Same sort of thing, hypercomplex rather than complex. Now, if you want to rotate by an arbitrary amount, you have you need to really to look at quaternions, at a quaternion. So if we have a vector, a 3-space vector, we want to rotate it by an arbitrary amount. The way you do that in 3-space, in a 3-space algebra, nicely in a computer game, if you've got a computer game and you want to have a little object that's flying through space and rotating and doing stuff smoothly, the algebra one uses for that are quaternions. Now, quaternions are pretty much exactly the same thing as we have here, but in 3-space, not in 4-space. So the quaternions are the 3-space part of the algebra which we're using here in 4-space. So it doesn't have the very nice properties that we get by mixing space and time, but it does have the properties you have in rotations in space. So that's what you use for rotating space. Now the quaternion algebra is a 4-element algebra. It's 1, I, j, k, where I squared equals j squared equals k squared equals -1, but also I, j, k, the combination of doing 3 rotations in the same sense after one another, also gives you a minus number, a -1 number. It gives you it in a different orientation. So there are things about that, and there are Berry phases involved, if there are any fields in there. Nonetheless, it's a very nice way, and it is the native way of doing rotations in 3-space. Now, what Innes was trying to do, for reasons best known to himself, late last night, was do a general rotation, as he should be able to do in Quaternion space, within the higher space, which is our 16-element space. And he was finding that the mechanics of that didn't quite work, and it's been bugging him for some time. So it has been Innes. The fact that it's been bugging him for some time means that the most exciting thing to do late at night, on a Sunday night, is to go in and see if he can fix it. Congratulations, sir. You become one of us quite a long time ago, but it's just lovely to see it in action. So he then has tried to find out what it is that's missing in the sandwich thing, which is what the Cambridge group introduced to talk about full rotations, but they're not really necessarily doing those rotations themselves and trying to implement them, but thinking about them in principle. So this is the Cambridge group arguing these things need to be sandwiched, quite rightly so. He's attempted that and found it doesn't do a general rotation for him. So he's thought, what's missing? He said, well, the fourth element is missing in this, because I've got the rotors. The rotors are the bivector part of this, alpha 1, 2, alpha 2, 3, and alpha 3, 1, rotation in the XY plane. So that's in the Z direction of the magnetic field, perpendicular direction for the magnetic field. So he's looked at that and he's found there is a bit missing, and what's missing is the fact that it's not a full algebra, in my view, a full Quaternion algebra. Now, the thing which is isomorphic means it does exactly, if you set those things up and do any maths with it, gives you exactly the same result in Quaternion as it does in the 16-dimensional algebra. If you restrict yourself in the 16-dimensional algebra to pivot and to the three components of the magnetic field, alpha 1, 2, alpha 2, 3, and alpha 3, 1, then anything you do with those four components, it matches exactly what you would do with the Quaternions. So that element, that sub-algebra, is isomorphic to the Quaternion algebra. When you get something isomorphic to the Quaternion algebra, you already know the Quaternion algebra will do any rotation you want, because that's what the computer gamers use to do any rotation you want in computer games. So that's what you need. If you're going to physically implement this thing and have it happen in reality, then you need Quaternions, at least. Now, the Quaternion algebra is embedded, and that includes the pivot in our algebra. And so what Innes has done here is he's rediscovered the wheel, but actually he's put the wheels on the truck here for the in the right place. So in terms of embedding that algebra and pointing out that one just can't get away with just putting a sandwich. One can get away with putting a sandwich, but the sandwich has to contain pivot elements as well. That's my interpretation of what Innes just said in longhand, because he was a bit quick about that. Is that right, Innes? Is that more?
Yeah, pretty much. So it was that kind of, just doing the sandwich thing with just the bivector, just a pure bivector on its own, so a plane, rotate something by 180 degrees. But if you want to, and yeah, like you're saying, I wasn't doing anything sort of different. It was more, all I was noticing with you is that when you put things into exponential form, everything I've seen it before has it as, oh, okay, you have a constant term plus the bivector. And just under your absolute relativity principle, so saying kind of you're not allowed to have anything just be a term on its own. Everything has a form. It's like, okay, well, pivot is in there then, which I just thought was fun for kind of pivot confining the electron, but also being there for rotating anything at all. It's kind of
this is just lovely, because the last version of that appendix was laid down in 2005. So if you have a look, you'll find it's kind of 2000. I think there were maybe a couple of beautifications in 2007, but nonetheless, we're talking 15 years ago. But of course, absolute relativity was thought about in 2014. So, so that principle is, so it's now beginning to apply the more up-to-date stuff of our stuff to some of the stuff that's sitting there as a historical document these days. It's pretty cool.
It's good fun.
Excellent.
I better send you the LaTeX for the appendix, and we can start updating it between the two.
Oh, that'd be good.
What do you reckon?
That would be good, because I've got a bunch of LaTeX of when I've been sort of taking snippets of it that I've been kind of poking at and doing bits and pieces. But yeah, I definitely wouldn't be able to take on the whole thing, because there's quite a lot of it.
There is. Nonetheless, there's no reason why you shouldn't have the whole source in the spirit of open source.
No, that would be wonderful.
Yeah, good. Yeah, brilliant. Okay, well, let's do that. I'll send it to you.
Oh, that's a good stop for that recording, right?
Yeah, good. Stop that recording.